Hello everyone. I'm going to walk you guys through how to look at Hess's law in terms of bond enthalpy. So we have looked now in class at Hess's law using multiple reactions, manipulating them around, and getting them to add together to create an overall reaction, and then adding the enthalpies to get the enthalpy of our final reaction. We have also looked at using enthalpies of formation. So those are values we looked up like in our textbook, and we were able to take our enthalpies of our products minus the reactants and find the overall enthalpy of the reaction. So we have one more method really that we can look at. Hess's law and enthalpy for reactions is really centered around this change in energy. And the change in energy is dictated by the bonds breaking and the bonds forming in our reactants and products. So here is a chart that we looked at. It's similar to one we looked at earlier this year, where we learned how to determine the bond enthalpy for a specific chemical. So I'm going to scroll down a little bit. It says previously we've learned that we can determine the energy it takes to break all the bonds in a chemical by calculating the total bond energy. We did this by adding up the energy of each bond of the bonds in a chemical as shown below. So we did this in our covalent bonding unit earlier this year, where we looked at our 3D structures and our hybridization and all of that stuff, and we also figured out that this is how we can find out how much energy it takes to break all of the bonds in a chemical. So for this one, we have a carbon-oxygen double bond, so I have listed that in my equation here, and two carbon-hydrogen single bonds. So we can use a table like the one seen up above and plug in the values for those or the enthalpy changes for breaking those bonds, and we can figure out that it takes 1,571 kilojoules per mole of this chemical to break all of the bonds. Okay, but that's only looking at breaking one chemical and its bonds. It doesn't show us how much energy it takes or is released when a bond forms, and it doesn't help us with our chemical reaction yet. So, since breaking bonds is an endothermic process or takes in energy that's positive, it's a positive value, okay? So that's why we get a positive value here, right? We're adding energy to break all of the bonds that are in this chemical. If we were forming the chemical or making the bonds, it would be a negative value. Okay, so if instead of breaking all the bonds, if I wanted to know how much energy was released to form this chemical, I would use the same value but make a negative. Okay, so that's how much it would take to form that chemical. It says since the breaking and forming of bonds is what occurs in a chemical reaction, we can use the same data to determine the change in enthalpy of the reaction. We do this by determining the total energy of the bonds broken, which is positive and endothermic, and the total energy of the bonds formed, which is negative and exothermic. If we add all that energy change together, we can determine the total enthalpy of the reaction. So we see an equation here, and it says the change in enthalpy of our reaction is equal to the sum of our bond energies for the bonds broken times N, and N is the number of moles of those bonds. So that's just like up here where I multiplied by 2 because I had 2 of that same bond. Same idea here. Okay, so we'd have to figure out what are all the bonds broken and how many of them there are and add them up. That's what this sigma means. That means sum of. And then instead of having to change the sign and make things negative, in our equation we just subtract all the bonds that are formed. Right? We sum them up, we add them up, we multiply that by that number of moles of those bonds and their bond energies, their bond enthalpies. Okay, so we're taking all the bonds broken and all the bonds formed, finding the total of each and subtracting them. Okay, so it says since the bonds forming is an exothermic process, those values are subtracted from the values of the bonds that are formed. Okay, so that subtraction takes care of making them negative or exothermic. It's done for us. So we have a couple of examples here. When we want to solve one of these, what's different here is that we need to actually see what bonds we're dealing with. So that might require you to use your previously learned skills of drawing dot structures to help you figure this out. So we're going to take this equation, CH4. So I'm just going to draw this out. I've got carbon and 4 hydrogens. All right, we've drawn methane many times. Plus 2 oxygen molecules. Oxygen in a molecule diatomic is double bonded, and I'm going to draw 2 of those so I can see that nice and visually. So those are going to be all the bonds that I break. Okay, these are my breaking bonds. And then the bonds I'm going to form is in carbon dioxide. That's one of our double bonded chemicals, right? It's got those lone pairs on the oxygen. The lone pairs don't really matter. We're talking about bonds forming and breaking, not lone pairs. And then we have 2 water molecules. We've drawn water plenty of times, those 2 single bonded hydrogens. But we have 2 of those molecules. Okay, these are the ones we're going to form, right? We're forming our products. So, we want to add up all our values to break and form all of these bonds. So what I like to do, you can set it up just like this equation, but we can kind of tally this up a little bit easier. So I've got CH, and then how many of those do I have? Well, I've got 1, 2, 3, 4 of those bonds. And then we're going to multiply that by the value from our table up here. So a carbon-hydrogen bond is 413, and up at the top it shows us that they are in kilojoules per mole. So 413. Okay, so we're going to have to figure out what that total is there. So 4 times 413 gives us 1,652. Okay, and then we are breaking these oxygen double bonds. And we've got 2 of those, right? We've got 1 there and 1 there, times, and we got to look up our oxygen. Now, this happens a lot in our chemicals where they just, or in these tables where they list oxygen by itself, because that's the only thing that's going to have an oxygen-oxygen double bond. So 498. Kilojoules per mole. So 498 times 2 gives us 996. Okay, these are all in kilojoules per mole. All right, so those are our bonds breaking. I'm going to go ahead and put my bonds forming in green here. So I've got carbon-oxygen double bond in my carbon dioxide, and I have 2 of those there, and I'll have to find my value. And then I've got this, I don't have a lot of space, oxygen hydrogen single bond, and I've got 1, 2, 3, 4 of those between my 2 chemicals. So I need carbon oxygen double and oxygen hydrogen single. So 745 for this first one, and where's my oxygen hydrogen? 467, 745, 467, 745, 467. All right. All right, so we're going to go ahead and multiply those out. So 745 times 2 of those bonds, 1490. Should have given myself a little more space here. And 4 times 467 for the oxygen hydrogen, and that is 1868 kilojoules per mole. Okay, now we're not done. We got to still kind of do our final math here, but we've got our totals, which makes it a lot easier. So we're going to take the bonds broken and subtract the bonds formed. Okay, so my delta H is going to equal 1652 plus 996. These are all in kilojoules per mole, so I'll put my units in at the end just to save us a little space right now. We're going to subtract the sum or the total of the bonds formed. So 1490 plus 1868. So my delta H here is 1652 plus 996 minus, I'm going to use some parentheses now, oops, 1490, that's a 4, and 1868. I get a total of negative 710, 10 kilojoules per mole. So what does that tell me? That tells me that more energy is released in this process. That's exothermic. So we are getting rid of extra energy, right? We released more energy when the bonds were formed than we took in when they were broken, right? So that is our total bond or enthalpy of our reaction. All right. It would be a good idea now to pause the video, see if you can at least draw out your reaction for the next one and figure out what your bonds are that are broken and formed. See if you can do this process and then come back and you can check it with me. Okay, so pause your video now. Try it out. All right, hopefully you were able to try this out and work through the problem. I'm going to draw a little line here, give us some space. So we've got nitrogen plus hydrogen making ammonia. So nitrogen, N2, is actually a triple bonded molecule. Let me draw it over here. We've got 3 hydrogen molecules. And again, I like to list them because it gives me a nice visual about how many of those we have. Another way you could do it, if you're comfortable, show you an alternative. You don't want to list all those. Maybe put it in parentheses in your 3 outside as a reminder that you have 3 of those molecules. So whatever bonds you're breaking, you have to times it by 3. Okay, so those are our 2 reactants. And then I've got 2 ammonias. Well, ammonia is NH3. Has that lone pair on it. And we have 2 of those. So we'll try this method. All right, I'm going to do my bonds broken in red here. So I'm breaking a nitrogen triple bond, one of those, and I'll look up its value, and a hydrogen single bond, but I'm breaking 3 of those. So I got my nitrogen and my hydrogen. So my nitrogen triple bond is 945. And my hydrogen single bond is 432. 945, 432. 945, 432. So this one, we get the same answer. And 432 times 3, we get 1296. And these are kilojoules per mole again. All right, so that's all my bonds broken. Now I got my bonds formed. So I have nitrogen-hydrogen bonds that are formed. I have 3 within my molecule, but I need to times that by 2 of those molecules. So I actually have 6 of those bonds. 6 nitrogen-hydrogen bonds. So I'm going to scroll up. My nitrogen-hydrogen bond is 391. So 6 times 391, we get 2,346. So now we want to put this all together. Our change in enthalpy of our reaction is equal to 945 kilojoules per mole plus 1296. Those are our bonds broken, minus our bonds formed, because forming a bond is exothermic, so we've got to make it negative. That's what subtracting does for us. We only have 2,000, well, just one number, but it's 2,346 kilojoules per mole. So we can do all of our addition and subtraction here. And I get negative 105 kilojoules per mole. So again, this is an exothermic process. That means we're getting rid of energy. So our reactants had more potential energy than our products did. We released more energy than it took in when we formed those bonds. So going down to your practice, It says use a highlighter or some other method to indicate the bonds that are broken on the reactant side and formed on the product side. So you might cross them out or highlight them. If it says something like CH2, those are going to be bonded on here. So you can always kind of move that around. We got 2 hydrogens bonded there, so keep track of those. If they're next to each other, like HCN, this one's redrawn for you underneath. And then over here we got HOC. Those are all bonded to each other, right? If it's just written next to each other, you can assume they're single bonds. This one shows a triple bond. It's labeling it for us. So we want to make sure we're keeping track of all of those bonds broken and formed, okay? Similar down here, we have CHO, CH2, that kind of thing. So you might want to draw this out, and check those things, okay? When you see these CNs, those are going to be triple bonds. Give you a little hint there. All right. I think those are the only weird ones I see. I'm just going to scan through, make sure there's nothing else odd for you guys. I think that's it. So there's 6 of them to try. There is one down here with some help or guidance. So you can use that QR code or the video attached to help you out. I'm also going to put another video with just some more examples on here as well. Okay? Thanks, guys.